Okay, so, all right, so let me share my screen. Stop sharing. I find that one I show you. All right, so okay, so this morning we were talking about tag. I guess I showed some examples. And these are like some semantics, as I said, like we have semantic, which is the meaning of like that tag, and then we can define whatever tag we want and say, okay, combination of these. For this project, I would say like we need to select which one we probably need. So I think the first for do not operator close, do not operator open. So this already includes these two, but if we want to use them, and then do not auto close, do not auto open. These are more for softwares that want to do some switching. Okay, so that could be used. And also we've got warning. We probably don't need that out of order, but this area should not be energized. I'm not sure if we need that, but I'm just explaining here. We have malfunction. It just gives a warning. Probably we don't need to be worried about that part. But this is stop and alarm inhibit. So I think we not gonna use alarms a lot. So, but yeah, still we can define and stop processing. We probably might want to use when the SCADA is like not good, so it's just chattering or giving some wrong results. And then this point test is also when we're doing testing, so it does not basically redirects all the alarms to somewhere else. So maybe we just take a note, Serena, I don't know, like create a list for them. We can put it in a design document, like
The
oh,
list and what we have in our setting default and
yeah.
compare to them.
Yeah, and then if we can, if they want, we can change that. So that's one thing. And from my presentation this morning, I think I covered this first presentation pretty much. Okay. So now we go to load flow and state estimation. All right. So this is kind of like an overview of maybe again it might be a bit repetitive from last week, but I will re-explain for the team to just refresh their brain. Like so, load flow is generally you have some loads or generation on the network, and so based on some other data on the system, the algorithm runs and provides results of like a current or kilowatt or kilowatt war phase angle for all networks.
You're not exactly sharing your screen on the unit. You're sharing the windows, not your desktop display. So it's your black screen.
It's from mine. Oh,
I think so.
okay.
So is it showing black screen? Or maybe it's wrong.
Xem đó, cái xem bằng cái nội dung còn có cái phấn chỉnh.
How about now?
Okay.
Is it? Can you see? All right. Yeah. Sorry for that. So yeah, so I was trying to talk about the load flow. So load flow, we use it for what if scenario. Um, and generally in simulation, we can run it in real time as well. But what does that what if means? Like what if means if, for example, we increase the load, or we close the switch, or we add this ER to the network, or change the set point of this. So some of this can be done by a user. Some of them can be done by applications, and the applications might run load flow a few times to get the answer for that. So this is the backbone. Load flow is the backbone of most of our application. That is, we call it model based. So that's why it's so important. So yeah, by user or applications could use load flow. When we do switching validation, when we, for example, try to open a switch or close a switch, again, in the background, it runs a load flow to see when we close that switch or open that switch, what would happen. And it gives us some warning, for example, if it's an overload or something. And so this, yeah, so freezer, so I think it's not in your scope, but like it's general. I was explaining this morning that like our applications in the ADMS and theirs are like using the same kind of foundation. So freezer video, or we have a dispatcher training simulator. So dispatcher training simulator also uses load flow. So for example, in the simulator, we say, okay, you shuffle the load or transfer the load from this video to the other one, automatically run the load flow and show how the measurement would change in the real time. You can see that. I think maybe you saw it last week. Also, forecast generated protection is not again in your scope, but also they could use load flow for you. DERMS. So, for example, we can have capacity, active network management, and look ahead. So FNA is for look ahead for future. They could use load flow when they are model based. What is the state estimation? So state estimation is basically, from some point of view, it uses the load flow input data, so static data like impedance or switch status or everything that load flow could use, but also utilizes the measurements. What is the difference? So load flow, you have a load curve, right? Serenia was showing you the other day, you can have a load curve. So that's like for a predefined scenario as an average, yeah. So, and then it's a typical day. But some days it might be different for whatever reason. So the measurement change. So the state estimation uses that measurements and adjust the load flow results to be close to the measurements where they can be, right? So it uses the measurements to make it more realistic, that the load flow results are more accurate. So let's see. And then for these ones, they identify the constraints of non-limited elements across the network. I think when we say constraint means like, let's say a conductor, a wire, overhead wire, or a transformer, or a breaker. These have some constraints, so you cannot, like, for example, run more than 500 amperes on this specific line I was showing this morning. So if it passes like those limits, it will kind of identifies them and shows the user. The third one is correction factor for loads. So typical load says, okay, 5 in the afternoon, like for example, like now like 1:49 in the afternoon, the load from the typical curve that you have, it says, let's say 200 ampere. Okay, it's just load flow says that, but your measurements this is 240. So it makes the correction. So 240 divided by 200 is like 20% more. It's just it will increase that to match them closely. In some occasions, if they're very far from each other, it actually might just not follow that and exit as a very different. Why? Because you might have a problem in topology or in data or whatever. So in those occasions, when the load flow results and the state estimation results are different, then it flags it. What is the other use case? I think in your case, you guys said you have kilowatt for feeders, but like in some customers that they don't have kilowatt, it can calculate it. So those applications such as forecast, active network management, load shedding will be using that. So why is it important kilowatt? Because nowadays, if you have a lot of solar, so it could have a different basic direction. It could go reverse loss and be down. So state estimation, it runs periodic. You can also run it on demand, but by change, or on violations as well. If the violation is more than something, it can show, but load flow generally it's either by on demand or other applications runs it eternally. So this is kind of like high level of this. Now, if we go to what is the input data? So connectivity model topology, I think we have that. Yeah, overhead line cable impedance rating. So for this one, I think the discussion was maybe we don't have it for everywhere, or we don't know. Customers would sometimes use like a default value close to this. How?
Cái mà super cáp mình cập nhật được đúng không? Với lại chờ lại cáp thì vẫn cập nhật được đúng không? Không, tụi em ý là nếu mà ở điện tập thì tao cập nhật cho em là loại cáp đó rồi xong rồi mấy cái điện trở của nó vẫn cập nhật được loại cáp mua hãng nào cũng đều có cái đó thì hệ thống OMS có, nhưng mà phần mềm tại của tụi em thì không dùng. Tụi em chỉ để cái limit dạy thôi chứ tụi em không quan tâm tiết kiệm nữa. Okay.
So how do you do that? Like, I mean, in GIS or other source of information, they know, like, for example, this conductor has this cross section, is aluminum or copper or whatever. They go to the catalogs or find, I use some calculations to calculate, for example, resistance. For reactance, it's basically spacing between the lines. There are some like applications that you can use and use some guess. Better than nothing, right? So, and then use the length.
If I don't have a cable impedance or that line characteristic, so can I predict make a forecast for my system? Okay.
No, like yeah, it doesn't.
If I have to take cable impedance or characteristic specification and I can make forecast.
Yeah, estimate. Yeah, but yeah, because yeah, you kind of guesswork. Yeah. Forecasting normally is for other terminology, but yeah, I understand what you're saying. It's kind of guesswork. Yeah. Plus, like we can use that as transformer. We're talking this morning rating of transformer you have already. Copper loss or I have like leakage impedance. You go to the sheet that you have it. These ones also good to have. We said about load profiles and solar. Solar panels, the capacity limit. Like for example, this is 5 kilowatts. Okay. But then in 5 kilowatt, how will we use it? By this, we have a weather signal says how much sun we have, like irradiation also. You have wind farm now. Wind turbine. Okay, right. So you have one energy storage, which is the battery, yes. But yeah, for it we have. Okay, so that is for load flow. State estimation with all of this plus this. So we could use current, active power, voltage, and as I said, better data. Okay. Maybe I showed this one on the diagram. Like I think did you see this one last week? Um, let me see. It's better to see it on the system, I guess. All right. So this morning I was showing you this area and I was saying these are results of load flow. How we do this, if we go to view, we have this icon here, LF results. So you see I, ampere, P is selected, so it only shows those two. And if we want to, for example, show voltage, it shows voltage. This is line to neutral when we say U. And like if we want voltage line to line, this is 12. So normally in three-phase system, we use line to line, but if you want to see per line, so you can use that. You could have Q, relative voltage, S, power factor. So if you want to see everything, you kind of like, but it's too much information probably. It's hard to read. So I prefer to select that one that I just want. And like say quickly no. And so the other thing is like in our system, you can choose the different things. Like if this is very small, you can change it to make it larger. So you go to configuration and like results, let's say, text drawing. Okay, so text drawing, you can change this size to make it larger. Okay, so for example, if I make it, you see, I don't know if you see in the note in the background, it's a bit larger than before, so you can, I don't know, make it super large if you wish. And the other thing, for example, you can change is here. You see, for example, kilowatt and ampere. Ampere shows 0.2. Okay, let me just make it a little bit larger for you guys to see better. So decimal point, I have 1 decimal point for ampere. For P, I have 0. But this is kilowatt. You could also have megawatt or something if you want. There is somewhere else you can change that. Then if you are interested only on one section, for example, like one element, you can right click on this and say show results. Where did I show results? I think my window, I guess, like it's too. Yeah, this is the resolution is a little bit difficult, but like, yeah, if it's on the bottom, so those menu you see is also everything is configurable. You can say, all right, I want this and that. But yeah, if you want more details, you can get that information. And this one is per phase. When you see on the display, that's the worst case. Let's say you have 3 phases and there are 3 phases, they have different currents. It shows the kind of like worst case. You see 191, it's actually L2, but L1 is lower and L3 is lower than that. So it shows the worst case here. And then you can double click this and close it. You zoom it out, it just keeps it like this. You can have more than this. These are handy if you want to analyze the results. Okay, so then yeah, you can look at these options, and lots of options there. You can see if something is not quite right for you. You can just search which area it is, or type something on the top, or go to the manual if you couldn't find it here. So to see how you change that. Okay, so that was the results for a state estimation. And load flow, it's one thing is like the results is the same. It depends on which one is run last. Normally in real time, we have a state estimation, but the state estimation is actually using load flow in the background, right? So it's kind of like, if you want to run it manually, you need to type, for example, load flow there, or you could go to DMS core. So you have this load flow icon here. If you want, depends on you, which one you prefer first. So yeah, so this one is the same. So you could like select, drag and drop here. Okay. And when you run this load flow, it runs it not just for that feeder. You see, MS01 is the name of this feeder that I selected. Like if I change the coloring, so if you remember this morning, I was showing the feeder, and that MS01 is the name of the feeder. But when you run load flow, it runs for the whole substation. So for all elements connected to that substation, and just it refresh the data with this one. One thing we can do when we run it manually like this, we can go to report. So we selected the report here, and then it shows all the information for all the elements, like for example, bus node, which is shows the voltage. For bus sections, it shows the sections like this. When you have this one is 3 kind of like, because you can go to one level up, this transformer area or the substation, or you can see like what is it behind. So that's like a 3, like one under each other, and you can close that and see the results there. But this one is tabular. When you say tabular, the good thing is like you can, for example, sort here as well. Like for example, I want to see on this Montana Sky substation, what is the highest loading in percentage? So if I right click that, click that. So, and twice, you see this little arrow here, it says that's sorted. And basically, because the triangle, the head is towards the bottom, it's sort, yeah. So this is the worst case in our scenario. So it has 81%. Okay, so this is on this feeder. And you can see this is the 3-phase, so 172, 187, 16. So maximum is maximum between this. So that 185, let's say, is compared to the rating of that conductor, and it is showing 80%. So you could also see any other things here. So the same for transformer, capacitor, energy storage if you have. Yeah, so here we're probably interested in the energy storage. So here probably they're out of service if they don't generate anything, so it's 0. But yeah, so any question on this one so far? So this is the report for this. Okay. The one thing we can also use is violations report. Right, violations. Is it S, I think? Yeah, so you can type it there, or again, yeah, that when you use the system more, probably you might really use that one, but yeah, we have these violations here, it's the same thing. What is the good thing about this, right? Load flow, you could go one by one and see what it is as I was doing, but you want to see what is the problem for your system. When I'm here, like here on the main root on this tree, it basically has information about everything on your network. And if something is red, that means you have violations on this, at least one. Okay, I have a lot, but okay, I don't want to just, probably I'm interested in this area in North America, let's say, or this substation. You can go to any of them, but okay, so if I go here, you see they change. In North America, like you see, a lot of measurements are a problem. But if I'm interested, for example, on the Montana sky, yeah, it's less. So okay, so I'm interested in the overload. Okay, I go to overload and you see transformer are okay, sections are okay, devices are okay. The only thing is violations is service transformer. And like you want to see more, so you kind of like expand that, and okay, you see this is like that. If you want to expand everything, you can also say, I would like to expand this. And then you can also use this filter to see, like just show me the a specific thing. Okay, so like if you want to see only high, if you want to see only critical, okay, so I just, for example, I want to see only critical. Limit violations is critical. I just don't want to. So where that critical comes from? If I execute, you see it doesn't show all of them, so I have less. Let's go to here. Let's go. Let's read these numbers, like to see what does that mean. So this is says it's 66 kVA. Loading is 131. Okay, and okay, if I locate this in our system, the substation, like distribution substation, we can model it like a box, but inside that box is actually the transformer and all of this. So it takes it here, but you don't see the transformer. What you need to do is just go here and go to internal view. All right, so internal view is this transformer, right? And I don't see any results right now. I say, okay, I want O, let's say, on this one. For transformer, we use S, right? So I mean, probably I can just to have just one result. Let's put S only. So you see, it's calculated 69 kVA for this, and if we go to catalog data, so this one shows like rated power 50 kVA. Okay. So that means this is higher than this, and that 130% that was kind of reporting was for this. So we have this rated power here, but on top of this, we have this overload limits. Okay, so these overload limits, as you see, we have defined 4. It is configurable. We can have 2, we can have 3, we can have 4. So, and some configuration, we have said, okay, use this 50% as normal. Like we can go up to that. And this is 10% above this. And this is 20% above this. And this is 30% above this. So where we define this, is here in the yeah, this space. So we go to the network builder, we go to telemetry editor, okay, and you see here in the detail it says 100, 110, 120, 130%, and normal, high, 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 critical. So I am not in the edit mode, but if I had opened this in edit mode, you see it says read-only mode. If I was in the edit mode, I could edit this. So maybe we take a note that like another thing that so we can check with them is this rated values. So yeah, I don't know. I take a note. We can just check with them. So do you guys think that these limits are good, or we need to change this overload percentage? I think maybe we just use the default, and if you guys want to change it, you guys can tell us. Maybe we need to wait for Mr. Fook, or maybe he needs to think. Okay, but I would say this is something to consider. Why? Because all of the elements in the network somehow could use this percentage. That example I gave to you, yeah, it was clear, right? So it's using this one as a base and calculates this one. And if user wants to say, okay, I want to change this, they can. So basically, and we call it override. So it says, okay, 50, I want to make it 52. You change it 52, you see we have this little rectangle here, and we say submit. When we say submit, it shows this here means that somebody override this. So when we override this and we run load flow again, it will use that 52 instead of 50, right? So, and that override, we can look at it. What is the use of this? For transformer, sometimes it has some problem during the, I don't know, so it has been overloaded. Carry the actual related load like before. Normally it's you rate it down. So you rate it down to 40%. You can say, okay, this particular transformer, they cannot do like 100%. It can go only 80%. And also for on and off, do you know what is on and off means? Like oil, yeah. So some this transformer distribution, but in the HVMV, you have fan for the transformer to make it colder, or you have oil, or you have air, so those type of things. You can go beyond the limit of that. So let's say it's 5 megawatts, you can go to 6 megawatt for a limited time. So you can use this one to play with that. And yeah, so you can think about this, how you want to use this in your system. But yeah, this one you don't need to worry that like the overload that I mentioned. And then if you overload something, like override it, sorry, override it, so you had a real value, you can kind of find them later. So like that's for this one. If I remove the filter, anything that I manually went and changed, we have a record of this here. So we need to open this limits override summary to see them. And here you can see what time I changed that, who did that, what I changed, and locate it. So yeah, so here, for example, this is something I did probably another day. So 11th, 1 week ago, probably, I was doing some changes. So is that clear? So about the overload and this stuff. So because they're all together, right? For example, this one is DR production. So for production, you can also say limit if it's too low. Sometimes you want to make sure your generators is contributing enough. Like this one is, you see, is 500. It should do 500, but right now it does only 100. That's why it marks it as low. They just note as well, if you see multiple low here, and just look at here, is this basically, this is a transformer area. That means you need to, there's one element on that transformer area. And then because level by level is hierarchical, so this feeder was okay. This transformer area had 3 feeders, like 4, 5, 6. Okay, 4 and 5, 6 were okay. 5 was low, and that's why we mark this low. And you can see the actual element is this one. So if we resolve this, you're gonna have okay for this one and this one. Yeah. So this is the way it is designed, this one. And you can also, yeah, kind of like, if you don't want to see this, you probably need to write a filter. But yeah, it's good to know. So that was violation reports. So for configuration, yeah, so I think we need to do this one. We have another report. This is again as a result of a state estimation and load flow, depends on which one was last run. Okay, so again, you can go through the one thing I just did today. I think, I don't know, you noticed, if I can like open one by one and go to the substation by one, or I just can type part of that name of that substation and it just takes you to there. If it's only one, it's just one. If it's more than one appearance, you need to go one by one. That's kind of like but yeah, okay. What this is report says? This report firstly give you some overview of what is happening for that specific area that you are highlighting. Okay, so this one, it says this transformer, this substation has injection about 18,900 kilowatts, about 19 megawatts. Okay, that's calculated. And then it negative 500 kilowatts capacity, and the power factor is close to 1. So why is 1? Exactly because I think it's fraction, right? So if this was a lot larger, probably you get a different number. So it has only rounded up to that. And this one, it shows your consumers' voltage are in this distribution. So this one, this demonstration, this system is based on 120, as I said. So 120 is normal. So it means like in this substation, about 2,380 customers, like if it's here, so these people are kind of like close to normal. And that's the, so this many people are below this, so you can go and just check, you kind of know what is the distribution. And then this is overloading. So this is pretty good. So you don't have much overload. So if the overloads was higher, it could suit this. And this one is for supply transformer. In our terminology, when we say supply transformer, we mean this HV to MV transformer. Okay, we say consumer transformer, which is like the distribution one, the one that goes to LV. So this is for that, and that's why we have 2, because in this one we have, I think, 2 or 3 transformer, let's say. And these are critical points on the system. That's the worst voltage as high, that's the worst voltage as low. And the worst section is 81. You remember I showed you from this report, from this report, I kind of like went there and then sorted this and I get the same results, remember? So this is kind of like faster way to that 81% that I was showing here. That's a faster way to know where it is, and it takes you to the same section. So it just gives you like a dashboard kind of like view, and the same for this. And you can click this to go to the violation report. So it's the same report as there. It's just a short key to go there. And the input balance is like this. So these are ampere, kilowatts, blah, blah. So you could see all the results for all transformer here. If you want to see the voltage and imbalance in the voltage, you could also go to the last page. So any questions for this performance? So I go to open this. This one's real time, right? So this one in our system, we have DMD. When we open DMD, it tells us where to go. So real time means the data comes from the field. So whatever measurements we see here is right now, it is received from SCADA and we get this value, okay. When we have a system like this, that data could come from a simulator, okay, network simulator. But what I'm trying to show to you guys is, okay, let's open DMD. And I want to connect to this system, PDS. Sometimes they have multiple systems you could choose. I go to this simulation. So simulation, you can basically say, okay, I want to study something. And right now it's selected all the network, but you could only select the area that you're interested, because if multiple users want to see this system, if everybody access to the same network, it's going to be too much load probably. But let's say I'm the only user, I have selected all elements. You can just, for now, but yeah, you could, okay, I'm not interested on, for example, this lab region. I can just remove that, right? Normally what we do, we just remove everything and just we add the area that we want. So let's say I want in North America, for example, for now, okay, and modify. It just creates that data. What it do, it goes to the server, extracts that data, and puts it in this simulation context. Simulation means, okay, it's not real time anymore. I want to do studies. I want to see if I do this, what would happen? That's what if scenarios that I explained earlier. Okay, so one thing, if you notice, the background changed color, so it's kind of like a dark blue. And the other thing you could notice here, it says simulation. In real time, it says real time. So if you want to, and also icons on the here is different. So, okay, it's pretty much same like view. The only thing is, okay, so here, let's get rid of this one for now. Let me go here on the view. I want to see I and P. Yeah. And then I want to go to here. So like do the feeder. Okay. So I have let's do the exercise that we did this morning. You remember we were trying, okay, something happens on this feeder. Like let's say there's a fault here, okay. And then I want to, let's say this is a fault. I'm saying this is a fault here. So I have to isolate them. When I do open here, it's not actually impacting the real time. It's just a study. So I have a work to do here probably. So yeah, so is I open these two switches. Okay, so this becomes de-energized. And let's before doing this, let's observe some of the results already. So just sorry before that. Okay. So here we have 3.4 kilowatts and this is 3.1 kilowatts. So load under this is 3 kilowatt. Okay. So I open this, I lose 3 kilowatts. And then here, if you see on this feeder head, we have 4.3. What I am going to do, I am going to see, okay, what would happen if sorry, I got lost. Where was it? Yeah, it was here, yeah, 3.1 kilowatt. So okay, I open this one and all right, so now this load is 3.1 kilowatt. I know I open also this one because, and then I go to the tie switch, which was here. You see, now it's zero. Why? Because there's high point, right? So there's nothing going through. So when I close this, you remember we had 3.1 kilowatts for that load. So now it follows from here. So if you notice, before I do switch here, so this load was 3.4, right? So 3.4 megawatts. Now, when I do this, so load flow calculations, okay, this load that we lost by opening this, it sums up here automatically. The 3.4 is the same. We didn't change anything here. Now this power and this power sums up here and we get 6.6 kilowatt. And if we go to the feeder head, we have this. So this is a what if scenario that we're talking about. And if we have put relative load here, we can see, okay, if this scenario happens, we can quickly see the coloring is pretty much normal, right? Except this one is a bit high. And if you remember this morning, I can use Control Shift L just for legends. And then this value is a 64. Okay, I don't want to just be using it visually. Like I want to know exactly what happens. So I go to this, let's say violations report. And I want, because the change I made was for this MS05, so this feeder only. So I'm interested on MS05. So I type MS05, and then I looked at here, say, okay, my basically overload is green, so I'm okay. The only thing is not green is this DR production, but this DR production was because of, you know, the value was low already. So it's not because of my switching. So that switching is okay to happen, right? So this is kind of like the way quickly you can say, all right, when I do some switching, is it okay or not okay? And like things like Fleasier, if we have Fleasier on the system, would run this automatically. The other thing that we do, so for example, you have a battery here. So this is zero, so it's not charging, right? So you can say signals, and then I already put some filters for make my life a little bit easier. So you can put any filter here, but I use non-custom. What does non-custom mean? So the signals that are not used by the applications are generally like the one that are non-custom. So this signal type here. So if you don't have this, there might be some signals that are custom. So I just normally select that to see, and then I see, okay, this is my set point, right? So this is the battery, and then I probably need to see something else. Okay, so this battery, the charging power is 500 and this charging power is 500. So you can do a few way to do this. So one way is just send a set point directly in this one, but I will show you, and for DERMS, I will show you what exactly other options are. But let's say for now, I just want to send a set point of 450. Okay. So yeah, you see that I put 450, that means generate 450. So it helps with the load flow now. So this section still kind of like green, but like, so it's not just switching, it's for anything like you can simulate, like this case, we do change the set point of the battery, and the application is the same. Let's say application sees some problem there, it would try to see what set point is the best to resolve that. So okay, so that's another way. The other way to use this load flow is I'm too fast, or you guys are following? So okay, so we have one feature called load scaling. Again, I typed it there because I don't know where is exactly load scaling. It's one of these icons. So what is the load scaling? Let's say you want to do some study, right? So you did that switching. Okay, it's good. You change your battery, it's good, everything is good. But you can say, all right, what if in the time that I want to do that switching, the load is more, like 20% more, because you want to have some reserve, right? So you want to say, okay, I want to be on the safe side. If you don't do anything, it assumes from load profiles, right? So load profile you already defined for each load is this, and it's kind of like average, right? Average for that specific time, right? Now you can say, I want to, instead of, and let's look at, remember like one results probably. So if it was MS05, right? This is not this value, don't look at this value, look at the results of load flow. So P and I. This one is 7 megawatt. I did the switching, is 7 megawatts. Now I say, all right, I want to go to, let's say 150%. Okay. And then you run a load flow. There's an icon there. It automatically runs load flow. And then when you go back to this here, if you notice here, so now instead of 7, it says 10 megawatts, okay? And that results is actually impacted here. You earlier had this one green, and sorry, yeah, green, and this one was like dark green. Now you see, oh, these are in trouble, like close to limits, and this is actually in trouble because you see is red, is 120%. So your switching in normal condition was all right, but if you simulated like 50%, you could say, okay, it might not be all right. So, and like, for example, maybe I need to put this battery in and see if it fixes it. So one way to do this is go to signal and increase the set point. So for this one, we can say, all right, we put 500 for this. Yeah, you see this one resolve, but this become kind of orange. So it's the over 120, it's 120. So it's not quite good, but okay, maybe you just keep going with adding more solar, more things, or you don't do that switching, right? So that was here. And also you could, instead of like increasing load, you can also manipulate the generation. So you could say, oh, what if my battery is not charged at the time? So I want to also study for this. So you can say, oh, no generation, and then run the load flow again. And this one, you can go back to, the red thing. So it's actually, it says 11 megawatts. It's because we had 500 kilowatts and 450 kilowatts. We lost that. So it assumed those batteries actually are generating zero. If you remember it, I simulate something here, but with the simulation of this, I said, okay, there is no that. And then the other option is, okay, I want to do rated generation or maximum generation, this kind of thing. So you can play with those values and do your study. That is what if studies that I was talking about generally. And this scaling could be done on different levels. Like I did it on the feeder level, right? So, and it shows it here. So it's 100%. And you could do on the substation level, on the whole substation level, everything. So you could go up to wherever you want. So the other option I have, sometimes scaling, I like this one because it's kind of comparable. You could say daily curves multiplied by daily curves. You can say fixed. What if my this feeder is I don't know, like 705 percent, or exactly, sorry, it's kilowatts. So 705 kilowatts. Okay, so that's also possible to run this and just see the results. Yeah. And if it's different from that, it's probably because it does some loss calculation and stuff like this. Okay. That is load scaling. And there are other things here, so you could use. Yeah, simulation setup. So what is simulation setup? All right, when I did that, it was actually for this time. This time was 2:57 p.m. Okay, what if I want to do this switching on Saturday and I want to do it at, I don't know, 7 p.m. You could like have a feeling of what is the maximum load in your system. So I don't know. Do you know what is the maximum time for your load? So when you look at the curve, what is the maximum time normally?
Maximum time, maximum load.
Maximum load is at what time? That's what
Maximum maybe from 8 to past 17 to 17, because if and when in the lunch at lunch in the cell from 11 to 11 a.m. to 13 to 1 p.m. is
okay. Yeah. So you could say, okay, I have this switching for the whole day because it's work happening. You want to maybe multiple days. You go of like what is the worst case time for you, and you have some feeling about it, and you put it there.
cũng thấy người biết sẽ có giờ để chưa được
So when you do that simulation setup, yeah, go ahead. Yeah, when you do that simulation stuff, it runs it for whole network. So that's why it took more time. And like you could see, okay, EMS failed, okay, and load flow, it has some warnings. But anyway, so this is recalculated for everything. So it's now is 8 megawatt, 8.4 megawatts. And okay, so this places that is failed. So we got some messages to see where it failed. So like in here, you could see there are some messages. Error is bad, right? Really. So and then you can see, all right, this is, for example, in this area, it failed. Why? Because the energization is unknown. I was explaining this unknown this morning. What could be unknown? What could be unknown is like you have connect, for example, one example is you connect air switch to a substation, and that cause this like here.
It's
Yeah, so this is not like
energy shock.
yeah, energy shock. So it cannot happen in reality. It's because of some data problem, I would say, right? So you could not have that. So okay, but that's kind of like troubleshooting of this. Like if you see some problem, like you could easily, I mean, like in general, easily, and see where that problem is. You don't want this happen, right? Sorry?
Can you add some yeah, a thing, a switch on this one?
Yeah, in the theory, it's software, you can do this. But what happened in some cases, the SCADA, for example, is wrong. Like it sends the wrong signal and it happens. And then you go there, see what is the problem, and you just find the problem and just fix it. And that's why I think even EMS failed, because even you see, I just removed this, but this comes from somewhere else. Even like I need to go and see where is this from. But anyway, so that's not the subject of our problem. But just for you, I think I wanted to say what does that mean, and yeah, why it took a long time, because it runs for whole network. That is the load scaling. I think I want to explain about a bit more about this. Um, I want to talk about load profile a little bit more. So let's put this one to feeder. So this is feeder head, and the load is kind of like, let's find somewhere is less complicated, like here. So the feeder, I think maybe yours also like this. It goes here, and then it branches out and goes to the users, right? So here, each of these little rectangles are a distribution transformer, right? And then this one goes to LV, right? So I right click and just go to geographic. So this guy is basically feeding, sorry, they go to LV feeder. So this one is network, yeah. Yeah, sorry, Alvin network is the one that I need to use. So this is like feeding this four customers, right? And what we can do here, we can right click here and go to show load profile. So load profiles means based on the data we have from those customers, it does some aggregation. So it aggregates those four, and then it shows the results in this. And that's for different time. It's from morning at 12 a.m. up to 12. So it's for one day, right? So for one day, you can see P and Q, you can see ampere, you can see production, you can see consumption. So if I like remove this production, that's total is probably, maybe they're on top of each other. That's why I see only one. I see only total. There was no DER, let's say. That's why it's 0 here. So that's why you have only C1. And you can also show the normal limit for this line. It's quite have enough capacity. We don't need to worry about this. So that's from what Srinia was explaining yesterday. We have the load class and the average load for each one. If I go to this one, like here, we can also load profile just for one single customer. That's for this single customer. And that customer, maybe I don't know, it's probably your load curve would be a bit different from this, but yeah, that customer is using 6 ampere at the maximum, 6.6 ampere on the maximum. And 6 ampere this, 6 ampere the other one, so it sums it up. So it shows it in this load profiles. So in this load profile, what you can do is change the date. Okay, say change the like, okay, I want to change it to 15th, for example. I want to change the temperature to 34. I want to, irradiation doesn't impact here because there's no DER, but like when I execute this, it shows a different here, right, based on the changes I have done, right? And then, so if you want to see more info, you can do the same thing here anywhere in your network. So let's say I want to know under like this, but it shows it for the downstream of this. So downstream, if you're not sure what it is, so you can always do tracing, right? So you can always trace downstream, but let's say I want to see here. So this is for that load. So this is like 200 something, right? And then on the feeder head, maybe you can see this. What is this network? MS04. All right. So we got some DRs here, so that's good. So load profile. Yeah, you can see this. You can run this in the real time as well. And then if you want to have some more information, you can see extreme points and stuff like that. Let's show this one in real time, so it might be more interesting there because you can have forecast. I think forecast we're gonna cover it later, but just briefly. So if you go here, you get 2 tab in the in simulation. We get only schedule. Here you get forecast and schedule. So schedule means just from load profiles, kind of static data. Forecast is from measurements and running in the background and stuff. So yeah. Okay, so one thing I want to know, so it's kind of like cover here. So these are from use of the system, but like how we configure this. Okay, load flow, there are something just to display, like I explained to you how you change the font, how to increase the font or like the units and stuff like that. So that's for just user interface, but like the behavior of software itself. Maybe Farhan probably explained about this profile library in general, but like you can go to configuration, right? File library, is it here? So yeah, or type profile library from here, or I think maybe anyway. So if I don't have it here, so I type profile library, profile is enough, just type profile. And then it shows like for different functions, like some folders like this. Load flow is the one that now we want to talk about. Let's see what kind of things we can cover here. Firstly, I explained the attributes and then maybe just I generally say why we have more than one later. Convergence limit. You know, load flow is an iterative algorithm. So when you run load flow, it does topology and goes to every single node. It has the load, like from load profile, so it curves multiply average, and then it calculates to see what would be on the feed ahead. But then it needs to consider the losses and stuff like that. So it needs to iterate a few times to get the results. In each step that it goes and run it again for itself, the error between two iterations, it should be less than that first parameter. So this one, and it's per unit, like, right? It's per unit. If the delta between these two iterations is less than this, it stops. So it's yeah, it's kind of like old load flow, kind of like they have kind of this convergence criteria. So if you like this one, we get convergence most of the time. Normally in distribution, we don't have much problem with the convergence. But if you feel like that it fails and it doesn't work sometimes, you can decrease, like for example, 1, 0 from here. It might be the results maybe a little bit less accurate, or so yeah, you can play with this. But I think we keep normally default, and normally for most of our customer, it would work. Oh, okay. So the next one is a bit complicated. I will show it with the simulation. Let's go to the next. Use LV equivalent. LV equivalent means sometimes you don't have LV networks similar to your network that you don't have LV. So what we do here, in this case, you model MV, right? So and then here on this transformer, I go to internal view. You would say the rest of this network, right? So you can have see the rest of the network. Just sum up the load and make a load equivalence on the secondary side of this. I don't need to basically calculate every single elements under that. I picked the wrong one, I guess, because there's no, maybe I go to the previous one, it's better. Yeah, this one. So this one, you gotta have, yeah, this transformer here, you see 1, 2, 3, 4, all of this LV network, they have like some loads. So we don't have that information. If we don't have that information in the system, instead of creating this LV network model, we just create this load equivalent and we add a value of equivalent as 6 customer, right? Because there are 6 residential, and let's say 1.5 is average of them. So you put 6 multiply 1.5 here, and then, or if you have it in system like this, if you have drawn it like this, the system does that aggregation. You don't need to do it by yourself. System would aggregate them, sums them up, and do this. It doesn't run load flow for that. Why? Because that's much faster. If you want to run load flow for those, the applications needs to go to every single customer and trace that network. So if you want to really go to the every single customer, some customers they do have. So you see, even if I turn on the results here, yeah, you don't see results here. Why? Because this load flow, you said I want to just use load flow equivalent. If you want to use like get the load flow to the LV network, you select the next one. And when you select the next one, you need to run it again, right? So you need to you see, when you turn it on, it took a bit more time, but it showed the results for every single LV part of the network as well. Yeah. So it's up to you, I think, and the information is if you don't have information, okay, we turn that off and we don't show that. So the line voltage for it is to display the results for all elements, line voltage for all elements. Do we want to calculate that? Yes, no? EMS results. So why we use EMS results? In our system, the EMS is subtransmission. Because in subtransmission, the network is kind of meshed most of the time. It's very meshed. The algorithm we use for load flow or state estimation is different. So we have another engine for EMS load flow. And when we select this, we assume that that load flow will be run and state estimation from or load flow from distribution would use that result. Why is important? Let's say you have two substations. One of them has phase calculated like 0. The other one is 0.2. When you want to tie between them, if they were 0, the calculation of load flow was different. If it's 0.02, it's a bit different. So in some cases, it might have impact, but most of the time, it's neglectable. So in your case, because we don't have EMS in the system anyway, so no need to select that, but just wanted to explain this. And these basically next one is capacitor status. If you have a capacitor that is not telemetered, the software does some calculation and guess if it's in or not in. And then in some cases you say, oh, okay, so it software calculated this is in, and it would assume is included. That's that one. This VR set point is called voltage regulator set point. So voltage regulator, I was talking about this briefly in the morning session. So what is set point here? Again, maybe for your system doesn't matter because this is the transformer. Let me just change it to the voltage level here. So you know what is this? So voltage, high voltage and low voltage. The regulator here tries to change the tap position to reach to a value that we set to this. Let's say this one is, let's see, this one I have a set point or not. Okay, so yeah, I have a set point, but this is in 120 per unit. So let's say is like so normal, okay, 123. So this is per unit, per 120 unit, let's say. And if we select that option, it calculates the tap position to reach this value, because that's what the reality of
in the distribution substation, we have regulating voltage regulating relay. So if I set in the set point on the voltage regulating relay, it's can automatic to control the tap changer to have the normal voltage to keep the normal voltage for this electrical system.
oh yeah, well, you have a voltage regulator on the MV feeder, right? So is it
in the transformer remote control unit? Yeah.
okay? Yeah, okay. So either way, either on those one or in the supply one. So it tries to guess this value. So if you don't have this value, like for example, it's telemeter, sometimes you don't have this. In the field, somebody goes and says, okay, this value should be follow like 120 ampere. Okay, that's fine. And then if you have this value, it tries to guess what is the set point set up for that. So I think, I don't know, like in your case, we need to have more information to see if we need to select or this or not. So I think right now, I don't have much information. Maybe we can discuss when you have more information on this one. And generation also, yeah, when you have selected this, let's say in this case, I have a set point, right? So I had put set point, and if I have selected that option, it will assume that, okay, it's set point, the battery or whatever it is, the ER, it follows my set point. Yeah. So that's why, for example, if I put a set point of, I think I did in the simulation, not here, but if I do it here as well, it would try to, but set point is okay. Let's say I put 100 kilowatt. Okay. Yeah, so for that one, you need to write a state estimation. You see, I put set point 100, and then it basically assume that set point is used by that. And if we have that option on, it will follow the estimated generation. So estimated by a state estimation. So, right. So we need to have the state estimation because, yeah, so it uses that state. The same is for this one. For all those three, we need to have a state estimation to be run first, and then it calculates that. Okay, so the first option I was explaining, automatic. So let's put in this one. Maybe it's here. Profile library. Sorry. Right. Okay, so I just select this. Um, Yeah, so that tap changing, okay. So, um, so what is that option that I was explaining? Maybe I just do it here so you can see what exactly it is. But this transformer on the one left hand side, you see that the measured tap position is 3, okay, and the calculated tap position is 3 as well. So let's say you got a load scaling, let's say. I think we have it already here. So sorry, I just go to MS123. Okay. So if we, in some cases, we go and load is increased. Let's say I want to make the load increased, okay. And then I run the load flow. You see, when I run the load flow and refresh this data, this basically, instead of 3, that is original tap position, it says 6. Why? Because when the load increases, your tap position also follows. Yeah. So this option that I was showing here is to based on like what happens on the network, local automation, because tap changer is kind of a local automation. So based on that, it calculated the tap position as 6. If we don't want that to happen, we can just deselect this and like, okay, so if I run a load flow now, the voltage would be different because this was trying to we see the calculated tab is as it is. So 6 is going to be 3. It's not going to change that. And you would see if I had turned on the voltage here. Let's put it like a V line, just make, and I just, yeah, it's 12.45, right? So, and then if I turn this on, okay, I apply that one and run it again because tap position is, so see the value changed. So it tries to keep the value close to the set point. So set point is here, is in, as I said, it's in this system. I think it's in, yeah, this 120 is kind of, think of like 120 is the normal, but it says it wants to be close to 135. So this is tries to get as close as possible to this, but with some bandwidth. So the bandwidth also is a parameter here. So those 2 Vs. So if it's below this, it just tries to, because in a certain step, you cannot exactly get to 123. Yeah. If you put 7 steps, it goes higher. Like you never get exactly to that. So that's the combination of that bandwidth and then this set point, it determines how that set point is calculated. Why we have this mechanism, especially this is important when we do simulation, because in simulation you assume that, okay, if your load changed, the tap position react to that and makes it in the limit. If we don't have this situation, the load flow is not like realistic, right? This is more for voltage. So probably in this case, in simulation, you would like to have this selected, right? In general, I would keep it selected. In real time, some cases you might say, okay, maybe I just want to use actual tap position all the time. If you want to use actual tap position all the time, in the real time, you may unselect that. Yeah. So this was this one. That's why I said it takes a little bit of time to explain it. And this one doesn't show in the real time because it uses this charge signal for batteries and stuff like that. In real time, it doesn't. I think it doesn't have it, and exclude service transformer. So if you don't have data about your service transformer, which I was showing here, so you don't know like what is the rating of this. This is again because there are many of these, and maybe in your database you don't have this, and it might cause a lot of problems, right? So in the violations that I was showing to you guys, it was many of them were like marked as like violations. Maybe that's data issue. We don't know. Like when you get, so let's see. When you get these overloads, you see there are service transformer. There are troublemakers here. Maybe the data is wrong. So it's actually load flow is good. So if you don't want to have, if you're not very comfortable with the data for your service transformer, you say, I want to exclude this. When you exclude this, then when you run this, it shouldn't mark them as bad. Here, I think the bad data is from supply lines, it's not there anymore from, supply service substation. Yeah, it's from supply points rather than the transformer themselves, right? So this one probably you need to look at to see why is complaining about that one. Yeah, but you can basically suppress that. I think probably in your case, you might need to select this one too, okay. Okay, so I explained this important information here. After topology, you want to trigger anything when the topology changes after set point change. When you give a set point, for example, to a DER or voltage regulator, it recalculates. These are more important in the simulation context. And these are the alarm setting. Do you want to get alarms or not? So for transformer, for sections, blah, blah, we can say, okay, we want to get alarms. So if you want to get alarms, you select, unselect this. So because inhibit means doesn't show. If you select this means don't show it. If you unselect means show it. Okay, when I unselect this and then I press apply, there's another configuration I need to just check to see if that actually creates alarm. So you go to configuration here, and here, okay, this is very important. So this is inhibit all triggers. Nothing happens in the back, like applications, not that things like state estimation and stuff like that. And this one is for alarm. So if you have this, also it doesn't matter if you untick there in the load flow. This is master, so that's why I needed to check this, but it's unselected. So these two are unselected. It just gives some delay, but we don't want on LV. So when we do this, okay, that means in 10 seconds, probably I get some alarms, right? Alarms. Okay, so I go to SCADA alarms. This is yeah, we have all of these alarms because of overload. Yeah, so you can see, all right, so this is overload, but this is look ahead. No, okay. So what we can do, we can filter. Look ahead is for, we're gonna discuss it tomorrow or something. Like, okay, I don't wanna see those one. Maybe I make a message. Doesn't contain, look ahead, okay. You can have more than one filter, right? So yeah. So probably we didn't have over limits here, so everything is in the limit. Probably if I change something, maybe we get it. But yeah, this was generally, yeah, you get the alarm there, I guess. If let's do this one because I think the reason is like I unselected this and alarms for service transformer. Okay, so I just want to show you guys like there could be some alarms.
uh, 11 seconds.
10 seconds, yeah.
10 seconds.
Yeah.
Is disappear.
Yeah, that it did not disappear, it appears.
Yeah.
So yeah. Um, okay, maybe we don't have alarms again. So I need to. Yeah, my filter maybe, yeah, it's just. Yeah, yeah, right. So I think the keyword is different. So you see loading. That's yeah, you can locate this one. It says there are some air alarms on this one. So yeah, you're right. So maybe. So it says loading, yeah. And also the source of this. So if you want to see is we see class DMS is one thing, parameter is from SCADA, and also source. We don't have source. If you don't see something here, you right click and just click here and source. You see power applications, and these are SCADA. These are like for measurements, but this is for source. The other thing you could do, our software, you can move this one across, and like if you want to see together, so you see this is high limits is from SCADA, so that's the measurement point, but this is from the application, right? And you can acknowledge. Okay. Let me see if we covered load flow results, violation reports, switching validation. I briefly explained, but maybe I explain again. Load scaling, load profile, we covered this. State estimation profile, we didn't cover this yet. So, okay, so let me go back to the system. I closed this alarm summary. Probably I return the alarm inhibit to what it was. Probably in your system, I don't know, maybe we can turn it on in future, but maybe at the beginning, maybe we don't need that, right? But like maybe the default would be section and transformer. We just can kind of like agree on it later. Okay. Let me just close this one too. Dashboard. Okay. Okay, so okay, let me manually close this. I think there's some problem in the background. So maybe I open too many applications here in this machine, or okay, we can close this. Take a break, or yeah, you can. Okay. Yeah. So yeah, I de-energized this whole network. Okay. And I think like I assuming there's a fault on this feeder, you wanna restore the feeder from another feeder. So here, like you got this switch, and when you want to manually close this, it goes to violations and says, all right, the first one is about just information that is energizing this and that. So if you go further down, you see this will cause overload measurements here. And this will cause overload limits on the voltage and all of this. So you can see that like the load flow is trying to calculate and where this happens, and you can just press this one and say, all right, where that happens. Yeah, so it just gives a warning that it could do this. If you do that, like then yeah, it's just a warning, right? You can say stop it, like you could say don't do it at all, or you can accept it. So that's also configurable. So we have our validation here. So validation setting is here. So you can go to the violation part and like select in case of like different thing what would happen. So for example, in case of overload, okay, so this is for overload. This is the messages that you would see there. So this cause overload on switching device, on the section, blah, blah. And these are in the GUMA, like it's basically after calculation, this will be populated. So you could, instead of warning, make it blocking. So if it overloads somewhere else, it does not allow the user to do that operations if you want. So, and like it's information, and instead of like the different color appears. So warning is yellow, information could be blue, or you don't want this happen at all. Like you can mark it as inactive. So if you don't wish to, because maybe the network is not ready, the data is not, it brings unnecessary user. So you can mark that as inactive. So, and you can do it on by folder. So I can just make all of this inactive or make all of them by warning. So you could do this, okay? And so yeah, that's the overload part of this. I don't know, like, do you think probably would you need that overload setting to be different, or you just not use it at this stage? Or if you wish, this is something they can always change during the different times. So we don't need to make a decision like what we need to do right now. So um, mm. Okay, so we've got half an hour there, or because I need to go to the state estimation, I think it would take time. Do you want to continue on the state estimation? I give some overview, or we move it for tomorrow. Maybe I just explain a little bit about load profile. Yeah, because this one, like, I would like to, I mean, probably cover together, but like, I can quickly go through a state estimation if you wish. Okay. Okay, so sorry if I glasses. Oh, I forgot something about actually, like this load flow, right? I said like we could have different load profiles. Did Farhan explain about how do you create multiple profiles? Probably not. So,
Yeah.
okay.
I think he already explained how to create multiple profile and assign the profile. Yeah.
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 Okay, do we need to, okay, if you don't need to repeat, don't need to, but yeah, it's simple. So you can just copy this one and create a new one. And then when the new one created, so just refreshing your memory, so you can do whatever you want here. And when it's finished, you need to press the approve. The only one that you don't need approve is the default one. So when you kind of like, okay, maybe I select this one, and I normally put a name that means something. So let's say LV, and then I approve this, for example. And I think for this one, probably it's better to remove this. And I approve this, and then profile assignment here. You can. All right, so you can do that. Okay, so you know this already, I guess. I don't need to spend too much time. So, but yeah, just refresh. You can assign and only, yeah, so you can say LV blah blah. So here. Okay, so yeah, so I think load flow, I think we have sessions to discuss about like how we tune the model, because it's not like you put everything there and it just results are reasonable. You need to do some tuning. We discuss about that later, but okay. From functionality point of view and configuration point of view, I explained the things related to load flow. We think we can just I think we can keep that as it is, and then we can change it as you want, and you can, okay. So state estimation, as I explained, the software, it uses not only the load profiles, but also the measurements. Again, the heart of the configuration for a state estimation is this profile. And it has many items. So to be honest, like going through all of them may take a lot of time, but this one, the first one, this is use only telemetry, or it could use other things. So when I say other things, could be, for example, calculation. So measurement verification, if you have current and power factor, use this one. Basic only is very kind of like limited. So I would suggest that like we just go with the middle one. It generally gives the best information for you. Quality of the SCADA. So any SCADA you get IEEE or whatever, there's some quality bits. If that quality bits are meaningful in the system, if we can say, yeah, use them. So if it's, let's say quality is bad, so it reduces the trust factor for that. This is the maximum number of iteration. This maximum iteration is different from load flow. A state estimation, when you run it first, it runs a load flow, and then it tries to adjust it to the measurements, and then run it again. So that's the iteration. So you could, two is working in general, so we don't normally touch that. What is this one? And these two together. These are together. So let's say we use daily as initial. So when we run load flow, sorry, state estimation in the background. So it just, for example, for this one, it goes and calculates the load profiles, and based on that load profiles and load flow, it gets some value, and that value. Okay, so for this point of the time, if I unselect this, it is, for example, total is at this point of time 15,000 kilowatt or 15 megawatts. That's the load flow calculations, and then that measurements, if it's close to that, if it's more than 3 times or less than 3 times of that value, it will ignore it, because it says, oh, the load profile is this and measurement is that. Probably measurements is too far. So, but if it's within that limit, it tries to adjust them between each other. Again, 3, I think it's kind of like maybe we make it sometimes 5 or 10. It depends. If we don't have a good load profile, we increase this. If we, during the time, we fix the load profiles and we make sure the data is kind of close, we reduce this. 3 is kind of like when the network is pretty much tuned. But yeah, we can change that value to 10 times or 5 times. So is it clear? So yeah, so the load flow says something, measurement says something. If it's 3 times of this, if it's out of 3 times of that, then okay, it's gonna not use it. So then we got this sorts of all of this value, absolute measured expected discrepancy. So when we say expected, measured expected is from load flow. So if the measured value versus the load flow expected value is more than 30, that means there's something wrong. So it reduces the usage of that measurement. And this is also actually calculated based on 20 kilovolt voltage level. The good news is for you guys, because your voltage level is 22, right? And the MV is 22, I think, or 20. 22, I think Mr. Fuchs said 22. So it's kind of this almost the same, but if for other customers, if they had 11 kV or something like that, they need to adjust it. So yeah, 30 ampere. So if it's too far from 30 ampere, it reduces. So if it's within that, it will use it. So that's for ampere. The same thing for relative. This one is in percentage. So you don't need to worry about the voltage level. Let's say your load flow says 100 ampere, 30% higher and 30% lower is kind of within the range. It will use it with a higher trust factor. If it's out of that, it just says, oh, okay, I need to use the other measurements to use this probably. So that was expected. Estimated is when you do the estimation and the measurement with the estimated value is more than these limits, similar to that, it marks it. It's just, this one is for marking the measurements is out of limit or not limit. So, and then for relative, I think I better to show a little bit on the state estimation results, because I know this is a bit complicated. So, and we unless we show you what exactly means, let me just do one and I just explain to you what it is. So, all right. Okay, this is completed. And then I go to the results of that. So now this is state estimation results at high level, but what I'm interested is this measurements, okay? All right, so it is the list of all the measurements, but what we have here, so the name of that measurement, so we need to know is MS4. All right, so then you can see the name is MS5 megawatt. Okay, so you remember this one, so you can copy this one if you want. And I can put a filter for object as this, just to a bit clarify for you what does that mean. Okay, so from left is object, the location, what is the type of the measurement is active power, ID, measured value. This is in kilowatt, 4.6, 4,406 kilowatt. expected is from load flow. These are pretty much close to this. So this divided by this is almost 1 point something. So it's within that 3 that I was saying earlier. So it is so the first test we have is this 3. So this divided by this is less than 3. It's fine. And then the next one is this one. The next test is for this one, but it's not ampere, but it is PQ. So it's IPQ is ampere, P and Q. So it will use this one, not use that one. So 30%, again, this is within 30% of that. So it's fine. It will use it. And the, you see this delta between measurement and expected. So this minus this is 107, right? And the percent is 2.4%. So this delta is very small. So it's within that 30%. So that's fine. That's good. And then the next parameter you would like to know is the estimated. So based on this, it will say, okay, I'm going to use this because it is comment also says correct. Based on that, I will utilize these measurements and for my state estimation. But then when estimates this value, so this is the third column, after combining these two with a lot of other things, it says, okay, I think estimated value is 4.5999. It's something between these two, if you see, right? And then the next columns here, so is the delta between measured and estimated value is 39 kilowatts. So it's quite small and it's acceptable. And measurement percentages, the delta is like 0.86, quite good. So then in reality, you might get different values because they are doing simulation, maybe it's better. So this is below that 20%. So it's marks it as basically good estimation. So state estimation quality for this one is marked as good. Trust factor is for each measurement, we can change the trust factor. What is that trust factor important? By default, we have like 80, and that comes from a parameter further down. Yeah, so this default measurement trust factor is 80. We can define some value between 0 and 100%. So if we think that some measurements are not quite good, we can reduce the trust factor to improve the results. Okay, I removed that filter for this guy, and you can see the results here, right? So you see, in this case, everything is kind of marked as correct, except this one not verified. Why? Because probably it's unknown on the network. Yes. Or maybe we didn't select to check that. So, but since everything is correct in the overview tab, you get this screen, and this little is for that unknown part, right? So this is for measurements. And do you have any questions about this? And this is measurement state qualities. Why we have this? Because state estimation runs in the background. So where we configure that? So we go to configuration, we go to the power applications. Is it here? No, sorry. I think that one is, sorry, it's just. Yeah, periodic is, sorry, here. The triggering for a state estimation is here. So we say periodic, run it periodically. So what is the periodic time? It's 900 seconds, about like 15 minutes, right? And like if the measurement change, what is this? So this measurement change, it uses these two first parameters, because measurement's always changing, right? If it's significant enough to change it, it waits 75 seconds to all changes to settle. Why we have 70 seconds? Because sometimes you do some open and close switch, all the measurement substation changes. So you don't want to run a state estimation 1 million times, because like you have a lot of changes happening. You want to, everything happens and 75 seconds. Why? Because one substation might come earlier, one substation might come a bit later. So you want all those changes to happen and settles, and then runs load flow. Normally, in the start of the project, probably we just go with periodic, we unselect this. And okay, you can do based on the weather data change, which we explained the other day. Like you could have like changes on the data. If the changes on data is dramatic, you can also select that. But let's just for now, just use it periodic. So, and then the master key, as I said here, so this inhibit triggers unselected. Then your measurements, the status dimensions runs in the background every 15 minutes. How you check that? So you could come to here and go to the measurement state statistics, and you can define the date. So for example, you can say from yesterday till now, tell me like what is happening. And it for this period of time that I selected, it says, okay, 50%, this is the number of time that was good quality, that was number of time that was kind of questionable, and so far and so forth. So you can have some details as well. So you could say for each point, what time you had good quality. So let's say I again, like if I want to sort something, I just switch to this tabular view first. And like, okay, I want to see how many times, what was the worst thing. So bad, we didn't have anything, but we have sometimes questionable. And those questionable is, for example, if I sort by this is 10%, this guy was 10% of time was wrong. So this is basically the measurements of questionable means like MVA. Yeah, it means like it was not quite close to each other. So the measurements and state estimation was out of a range. Yeah, so this is also when you have the system running, like you could use this data to see how a state estimation behave over the time for your system. So just to show the state estimation results, like overview, we said what it is, right? So it just also gives you some statistics of how many measurements you have. So 15 total telemeter, 3 ampere for P, for Q, blah, blah. You can see all of this. And non-telemeter is like calculations. So we didn't have any kind of calculations. Verified. So when it says verified, probably sometimes you cannot verify something. It just, that's one of them. It doesn't work. So that's why this is unknown. So that's the unknown one. You couldn't verify that. And individual is kind of like gives like a brief overview of that feeder. So if you have, for example, go one level up, you could see more information about here is yeah, you see like the one that we selected, they have different kind of comments and it's quality. So quality, for example, for this one is a little bit questionable. We don't have anything bad, but we have some questionable, let's say for the first one. And you could dig more to see what was questionable and stuff like that. So that's the overview. And then measurements, I think I went to very details of this. One thing I would normally check on this one is like I read the comments, like, and the quality of this. If it's unknown, I filter. Okay, so okay, want to see what is bad. Okay, so that's the first thing. Okay, that's good. We don't have anything bad. Okay, but then you can see, okay, what is questionable. And when you have some questionable, you can go and just verify that why that is not that's questionable. Is it because okay, let's go there. Yeah, this is questionable probably because you see the measured value is 0, expected is 0. So maybe like we have some kind of problem with the model or something. So yeah, it could be that. So this is even we don't have it in any locations. When you don't have location is like not highlighted like this, it does not belong to like display. But again, okay, you can just go and find it. Okay, so you see it's kind of like on this one. It's not connected to anywhere, so that's why it just complains about like their not good results. It's yeah, these are 0 because this side is not connected to anywhere, so it's not a problem. So in this one, sometimes if you say questionable, you need to just check that what's going on, and if it's not a problem like this one, you can ignore that. So any question for this? We go another time for tuning, another session. So I think from high level state estimation, you get some feeling at what it is and then what it would do. And I suggest that, okay, so let's use the state estimation, this default one at the beginning. And when we do tuning, I think I might come back and just explain more about this, how we change some of this when we do the tuning process. So from like configuration point of view, I guess state estimation, the main thing is in the load profile, right? So this is in the profile library. And also, I show you one example factor. So let's say this measurement, let's assume is kind of faulty. You can go to control value, all right, and say, okay, this 4.3, I think it's faulty for whatever reason. I mean, in this case, it says quality good, but okay, I just assume. So you could just change the trust factor not to be used. So then in the calculation, the state estimation would not use that one, and you can say enter. So this is again another thing you could do, but individually. Also, you could actually do it from here as well. You could here you see you can do trust factor. Here you can change the whole feeder. I could like say, okay, I want to change the whole feeder by this one. Yeah, set trust factor for all the measurements shown on the display. So which is kind of like probably I wouldn't do it unless we know that the whole feeder is wrong or whole substation is wrong. So if I hope substation is wrong, I go here and say, okay, just change everything to something. This change gives you a warning. This will impact 15 measurements. It impacts all of this. Or you could filter it actually. You could say, I want to do for kilowatt like measurement type. So type is measurement. Okay, so I want to see, okay, kilowatt sometimes is like, it's funny. Reactive power. Okay, if you only have this, you see, when you apply this, it applies only to kilowatt, not to everything. So I can say, okay, I want this to be used. All right, instead of 80%, okay, you can put in value as well. So it says, okay, it's default. I want to, instead of 80s, okay, I want it to 20. Okay, so I do 20. And this is done. All right, so if you go to here and refresh it, so This one, yeah, it's 20. This is calculated trust factor, so that's different. So. Okay, so yeah, we can conclude, I think, today's, I think let me just check something here to see. So we discussed this. Oh, it's a tuning process. We come back to this tuning when we explain the tuning part. So, all right, so I will explain this one later. Okay. Any questions, guys? Yeah, no question for now.
Just to understand this system more than I was.
It's new for everyone. Is new. I think yes. You guys more experience. I think from different projects, other project managers. But yeah, it's kind of for you. It's good to know about